Alright, so I think I'm recording here. What did I do with my tablet? There it is. Um, we're looking at scale packet 5, which is exponential functions and logarithmic functions. In skill 5G, we're looking at, again, at solving equations, and you must know your properties of logarithms and the definition of logarithms in order to solve these. Here in problem number 3, they give us an exponential equation. When our variables are up there as exponents, we really don't have any properties of equality that will let us isolate that variable. So that's where logarithms come into play, because if we take the log of each side, then by the product rule, we can pull these exponents down as coefficients. So since we're going to approximate our answer once we get it using a scientific calculator, we need to either take the common log of each side or the natural log of each side. So let's take the common log of each side. We'll get the same answer whether we do either one, so it really does not matter. If I had a base of e, I would definitely take the natural logarithm, because then it would just make the solution a little bit quicker and easier. But again, it doesn't matter. We'll get the same answer either way. So now that I take the log of the left-hand side, I've got to take the log of the right-hand side. By the product rule, these exponents come down out in front as coefficients for multiplication. So I have x plus 4. There's one factor times the factor log of 5. And then I have this binomial that comes down. Here's the factor on the right-hand side times this factor of log of 25. Well, so I need to get the x by itself, and I have the variable on both sides of the equation. So I need to rewrite the left-hand side and right-hand side so I have terms that I can get the term that has the variables on one side of the equation and the terms that do not have a variable on the other side of the equation. So this binomial is being multiplied by this number, the log of 5. I need to use the distributive property and multiply both numbers of the binomial by log of 5. So I'm still going to have a binomial. I'm still going to have this addition, but the first term, instead of it being x, it's going to be x times the log of 5. And the second term, instead of just being a 4, it's now 4 times the log of 5, because that log of 5 multiplication just distributes over addition, and it distributes over subtraction. So on the right hand side, we do the same thing. Instead of just writing 5, we have 5 times the log of 25 minus x times the log of 25. Oops, 25. All right, so the two terms that I have of interest are the ones that contain my variable. So I need to get those terms on the same side of the equation and these constant terms together on the other side of the equation. So I'm going to leave the x log 5 where it is and add x log 25 to each side, because the opposite of subtraction is to add, so addition. So I've got the x times the log of 5 plus x times the log of 25. And so now the two terms that have my variable are on the same side of the equation. And if I subtract 4 times the log of 5 over here, alright, so now when I look at these two terms on the left, they have something in common. They have that variable x in common. So I can factor that variable out. And I have log of 5 plus the log of 25, and over here I have this. Now I'm not going to, I could write this as a single logarithm. I can take this 5 and pull it up as a exponent, and that 4 pull it up as an exponent, and then the division write it as the log of a fraction. But I'm just going to leave it like this. I mean, there's no reason that we have to do that. It doesn't make it that much easier to key it in the calculator. So I'm just going to leave this numerator like it is. And I say numerator because I'm going to divide it by this other factor Now, this guy, this log 5 plus, now I can multiply it. 5 times 25 is 125, and that's pretty easy to do. So I just went ahead and did that. So even though these look different, these are the same, and they divide to 1. So I've got x is equal to, my exact answer is this 5 log 25 minus 4 log 5. And remember, those are common logs, and so is this one. Now, it doesn't mean log times this. There's no way that I can come in and cancel any common factors. I want to jump to my calculator now, and oops, well, maybe I'll just leave it like this, and give a decimal approximation to this, at least to 3 decimals. And so I'm going to put parentheses around my numerator, so that when it divides it divides the whole thing, not just the second term. So I've got 5 times the log of 25. Now the calculator put in the initial parenthesis there for me. I have to close that, and then minus 4 times the log of 5, and divided by the log of 125. Alright, so I'm getting 2.000. Alright, now is this one that's, yeah, this is one that's fairly easy to check. If we plug 2 back in, on the left hand side we've got 5 raised, well, 2 plus 4 is 6, 5 raised to the 6th power, and on the right hand side we've got 25 raised to the, well, 5 minus 2 is 3, 25 to the 3rd power, and hey, we get the same value, so it checks. So, and it looks like it was also an integer answer, not a decimal answer, which pretty nice too, huh? Alright, so let's check on the next equation. We don't have a log equal to a log like previously, so I want to use the definition of a logarithm to convert this log equation to an exponential equation. But before I do that, well, I could do a couple things. If I raise the 2 up as an exponent, or why not just divide both sides of this equation by 2? Because the factor of interest is this log that contains my variable. So why not just go ahead and start right off and divide this by 2 to get this factor by itself. And now, since this equation is in log form, I could rewrite this as log base 2 of 4, but it's probably just easiest to say, hey, this is in log form, the base is 2, a logarithm equals an exponent, so 2 squared, and that's going to equal this argument of 3x plus 1. 2 squared is 4. Subtract 1 from each side, and you can see that 3 plus 1 is 4, so x has to be 1. And that doesn't produce log of 0 or log of a negative number. So hey, that's our answer. Now, to check this is a little more difficult because I don't have a base 2 button. I'd have to use a change of base formula on my calculator. It's not that I can't do it. But when you plug it in to check, let's write it out over here. If I have 2 times the log base 2, plug in 1, and you've got 3 plus 1, which is 4. And the question is that equal to 4? Well, I don't think we need a calculator at all to do this, because 2 raised to what power is 4? 2 to the 2nd power is 4. On the left-hand side, this is saying 2 times 2 is equal to 4, and on the right-hand side, it's saying we have 4. Hey, that's a valid statement. So our x equals 1 definitely checks, and I didn't even have to use the calculator. Alright, so let's move on to the next one. So here we have an exponential equation. On the left-hand side, I have 2 terms. The term that has my variable, the term I'm interested in, is this first term. So the inverse of adding 6 is to subtract 6. That's what we'll do to both sides of this equation. Oops. And 5 to the x. If I subtract 6, 4 minus 6 is a negative 2. I've got a problem here. There's no way that I can ever make this base 5 raised to some power equal to a negative number. The range for an exponential function is positive real numbers. Negative exponents don't make our answer negative. This has no solution. There's no way that we can find any value of x that's a real number that solves this. Alright, so I hope that helps, and I'll do the next two in a pair. Talk to you later.